it would go from me reading the textbook to you guys just watching me sleep. Because sociology is just, it drives me nuts. I have a psychology textbook, that's more interesting, and I feel like that's probably more practical to a lot more people. But I was like, no, I should make it kind of like central to my degree. So I was like, okay, so it's gotta be a chemistry textbook. And once I limited it down to that, the choice became obvious. Quantum chemistry. So I chose this textbook for several reasons. The main reason is it's actually my favorite textbook that I own. Not because it's interesting or because the content makes sense, which it doesn't, and it's just like how the electron like behaves in a certain confined space. That space being, so when they say particle in a box, it's technically a more accurate way would be like an electron in an orbital, I think is what they mean. But even then, that's kind of inaccurate because an orbital is just a probability area where like the electron probably is, because as this book talks about, you can either know an electron's momentum or its position, but never both. And even then, it's never like you're sure you know the momentum or position. It's like you have a good idea, but you could never be sure. Maybe if I can find that, we'll talk about that. Chapter 4, the postulates and general principles of quantum mechanics. Fun stuff. Chapter 5. Oh no. The harmonic oscillator and vibrational spectroscopy. I remember that. That thing was horrifying. We had to do an experiment on that, and I think we used I think it was an infrared spectrometer. And, I mean, it looked really cool, but it was a nightmare. Basically, this is entirely mathematics, so it's like, you'll do like a 5-minute experiment. I mean, like 5 minutes. You'll do a short experiment, and then for like the next 10 hours, you're basically putting numbers into Excel and trying to make the equations work, and you're rearranging formulas and all that. Chapter 6, the rigid rotator and rotational spectroscopy. I don't really remember that one. It rings a bell, but I don't really recall it. Chapter 7, the hydrogen atom. Good atom. Hydrogen atom. Very interesting. Has an s orbital. 1 proton, 1 electron. And yet, most of the time, it doesn't even have an electron. It's just kind of, wow. Okay, that's inaccurate. So, pH, which is, as you know, a measure of acidity and basicity, or alkali, as some people call it, is just a measure of the concentration of proton ions in a solution. And so when we say stuff like H+, it's technically H3O, which is just H2O water with an extra proton. Because you can't actually have just like a free floating hydrogen plus atom. But we just represent it as H+ because it's faster than writing H3O+. Okay, so that was chapter 7. Chapter 8, approximation methods. Yeah, this entire thing is just approximation. That's all it is. Chapter 9, many electron atoms. Not too sure what that is referring to, but okay. Chapter 10, the chemical bond. 1 and 2 electron molecules. I don't think we even got that far. Because that talks about the Born-Oppenheimer approximation. And I don't think we decimal places. Oh, man. You want to talk about blissful ignorance? Scientists at the end of the 19th century must have been awesome being them. Because now everyone knows what they don't know. These guys didn't even know what they don't know. But we're like, no, we don't know this, but we know we don't know this, which just makes it all the more infuriating. This attitude was somewhat justified by the great advances that had been made up to that time. Chemists had finally solved the seemingly insurmountable problem of assigning a self-consistent set of atomic masses to the elements. I'm trying to define what that sentence even means. Insurmountable problem of assigning a self-consistent set of atomic masses to the elements. So I guess they just assigned atomic masses to the elements. Which I guess, yeah, that's a big deal, because when was the periodic table designed? I'm not sure I remember. But yeah. Skip that. Oh, hey. The great work of Dmitri Mendeleev, I think it's Mendeleev, had resulted in a periodic table of elements, although the underlying reasons that such periodic behavior occurred in nature were not understood. So they knew the periodic table existed because Mendeleev had made it, or designed it, or arranged it. What would you call it? Anyway, and he was doing, stuff, and all of a sudden all these patterns started arising, and because I think there was an instance, I wish I could remember the name, my organic chemistry professor told us about a guy who, this was early on in the periodic table, but he noticed a trend, and he was able to calculate an element that hadn't been discovered yet. He was able to calculate like all this stuff about it, like its density and all that stuff, and like all its like reactivity and stuff. And then a couple years later, an unknown amount of years later, the element was discovered, and he was like dead on. And they're like, oh dang, that's awesome. The fact that, like, I'm looking at my periodic table right now, the fact that, these trends arise when you design the periodic table just like this, and it's pretty cool. Okay. Let's see. I can skip that. Okay. I can skip that. Okay. In the related field of physics, Newtonian mechanics had been extended by I'm just going to pronounce it Joseph Louis Lagrange and Sir William Hamilton. The resulting theory was applied to planetary motion and could also explain other complicated natural phenomena such as elasticity and hydrodynamics. So I'm actually reviewing physics right now, and I gotta say, like, it is remarkably just like wonderful how in an ideal system there's like 5 equations that you can use to calculate all this stuff, and then like by deriving or like just swapping up the formulas or like adding in just like the equations for force, you open up all these things just from these 5 equations, and like they're so simple. Like you just be like, what's your initial velocity? This. What's your final velocity? This. What's your acceleration? This. Oh, okay. Here's how you calculate the distance that you travel in however amount of time. And it's just like, it's remarkably simple. the slightest. Like, I understood it, but I couldn't, like, I was really bad at it. I understood the theory, but I couldn't understand the practice. That's how I'm gonna put that. Oh, Gibbs. Heck yeah, we're gonna talk about Gibbs. The Gibbs free energy is probably gonna show up at some point in this. Yeah, I'm trying to find the interesting bits. Black body radiation could not be explained by classical physics. Okay, just a second. Oh, okay, let's see. The series of experiments that revolutionized the concept of physics was concerned with the radiation given off by material bodies when they are heated. We all know, for instance, that when the burner of an electric stove is heated, it first turns a dull red and progressively becomes redder as the temperature increases. We also know that as a body is heated even further, the radiation becomes white and then blue as the temperature continues to increase. Thus, we see that there is a continual shift in the color of a heated body from red through white to blue as the body is heated to higher temperatures. In terms of frequency, the radiation emitted goes from a lower frequency to a higher frequency as the temperature increases, because red is in a lower frequency region of the spectrum than is blue. The exact frequency spectrum emitted by the body depends on the particular body itself, but an ideal body, which absorbs and emits all frequencies, is called a black body and serves as an idealization for any radiating material. The radiation emitted by a black body is called black body radiation. Pretty simple, like, naming schemes that physicists have. It's like, oh, this is called a black body. It emits radiation. What do we call the radiation? Black body radiation. You know who's terrible at naming things? Biologists. Don't let them name things. Because I might sneeze. If so, I'm sorry. Because there's like a protein in your, is it your nerves or something? And it has something to do with like electrical conductivity or something, electrical impulses or something like that. And so it's like, what are we gonna call it? I know. Let's call it Pikachu. Yes, as in Pikachu, the electric mouse from Pokemon. Yeah, anyways. Oh, there's a bit of a graph here. I wonder if I can show it. Okay, so, oops, those are a bunch of equations. So, oh man, yeah, you can barely see that. Okay, so, this one right here, you see how it's kind of like three waves built on top of each other. So the top wave is, so all these are related to temperature. I don't know the exact units they're using, but I think it's a temperature versus wavelength, if I had to guess. I don't recognize these units, but I'm gonna go with temperature over wavelength. Yeah. And so each one of those waves corresponds to a temperature. And so the one that was the highest, that is the highest temperature. The one that was the lowest, that's the lowest temperature. And it's basically just showing that as the temperature increases, the light emitted is more intense, or the radiation emitted, as they would say. Okay, a bunch of derivations. We don't want to talk about that. Some experiments. it's got 3 M's in it. So obviously we have to shorten it down to just the letter P. I'm sure it's some Latin thing or something like that, but it's like, you're killing me here, physicist. That's the problem with having only 26 letters. It's like, you can use capitals, but, you know, it's like, we got V for volt, V for velocity, V for volume. Well, I mean, technically V isn't used for volume. It's just used to indicate where you put the volume. Because you never describe something as being like, oh, it's 20 volume. It's kind of unrelated. The Broglie waves, yeah, more interesting. Oh, and then Planck's constant. It's a very, very, very small number. It's like 10 to the negative, like 31. It's a very, very small number. Yeah, that's the thing. Planck, he worked with like very, very tiny measurements. Hence Planck length, and stuff. Yeah. The Heisenberg uncertainty principle states that the position and the momentum of a particle cannot be specified simultaneously with unlimited precision. So I wonder, do they show it? Yeah, okay. So, the change in position times the change in momentum is greater than or equal to Planck's constant. And so, basically that's just a simple rearrangement of, if you want to find the change in momentum, the change in momentum is then greater than or equal to Planck's constant over the change in displacement, or, yeah, the change in position, or displacement, I suppose it would be called. And then to find the change in displacement or position, again, same thing. Change in displacement is greater than or equal to Planck's constant divided by the change in momentum. This course was like, so it was actually taught by like one of my favorite professors. Not because I ever did good or well in his, I never did well in his classes. In fact, I usually scored like in the 60s. But I liked him because we got along really well. But like, basically you would enter his class, and like for the next hour or hour and a half or however long his class was, you were gonna be writing the entire time. Because he would basically, he'd walk in and he'd grab the marker and he'd just start like writing, and you would just copy like, yeah, word for word. And it wasn't until like my final like class with him that I realized like, going through, you could just like cross out entire pages, because he was like, because you could basically just look at it and go, okay, there's literally nothing you could ask us about, like on a test, about any of this, so just, and then just, and once I learned that, like my final test, I just like, because I knew I could shorten down like this many notes into like 3 or 4 pages, and it just like, memorize those, you're good to go. Okay, so these are the practice problems, which we are not gonna do. That would be too much for me. Okay, let's just turn to a random page and see what kind of mischief I can cook up. it covers the entire cube, because obviously, yeah. Oh, they have matrices in this. Ooh, matrix. Oh, I hated matrices. Then again, my professor was awful. He was like a fresh PhD student. Like he just got his PhD and he was teaching the lecture, and oh, he had an ego on him that just made him impossible to deal with. Like everyone was just like you'd ask a question because he was unclear, and he'd look at you like you just asked him like, why does 77 plus 33 not equal 100? And you would just be like, I don't understand this concept, and just like he'd look at you like you were an idiot, and it was just like, that's not helpful. You're not helping right now. Oh yeah. Then phasing was fun. Okay. There's no way you're gonna be able to see these equations, but it is entirely like Greek. Like there is not a number in sight. Like the running joke was like, whenever the professor was like writing out an equation, he'd occasionally like write squared, and we'd all be like, a number. Behold, math has numbers again. But yeah, like we would all call it Greek class because we'd just be like, what Greek letter are we gonna learn today? Okay, I gotta find something to read. I haven't actually read anything in a while. Problem is, it's explaining all these derivations. Okay, maybe if I go to the beginning of a chapter, that will help me. Oh, here we go. Oh, I just noticed that it has like little like biographies at the beginning of every chapter regarding a certain physicist or whatever. Okay, here's something. The rotation of a diatomic molecule can be described by a rigid rotator, which is like a rotating dumbbell. Using the concept of a reduced mass, we can picture the rotator as a body of reduced mass, mu. So it's like that, it's like an M and a U had a baby. Rotating about a fixed center. This problem lends itself naturally to spherical coordinates, and the wave functions are functions of theta and psi, the two angles in spherical coordinates. The wave functions are called spherical harmonics and occur in many problems involving a fixed center. In fact, we shall see in the next chapter that the s, p, d, etc. orbitals of a hydrogen atom are described by spherical harmonics. Solving the Schrödinger equation for a rigid rotator is a fairly lengthy process, yeah, to say the least. And so, in most of this chapter, we shall simply present and discuss the energies and the corresponding wave functions. We shall use the allowed energies to describe the microwave spectrum of a diatomic molecule and see how you can determine bond lengths. Yeah. Oh, actually, that reminds me. This is a fun fact I like. So, depending on the energy level of a wave, so like microwave, gamma wave, X-ray, it can make a molecule do different things. A gamma wave, okay, so infrared causes it to stretch. Infrared waves cause bond lengths to stretch. molecule and it heats it up. Remarkably lovely. It's just perfect. I don't know, I thought that was a fun fact. Yeah. So, quantum chemistry. Yeah. I kind of want to do this again, but with a textbook that I can actually read, as opposed to just trying to describe equations. I don't know how much actual reading I did. Might want to work on that. But, yeah. The way I see it, I either just bored you to sleep, or if you're a nerd and you just like hearing me talk about random scientific facts, then you're probably not asleep right now. Or maybe you just need background noise while you're doing something, in which case this is a pretty good background noise. Yeah, maybe next time I'll read like biology, or you know what, I'll probably just read like a first year chemistry book. They're relatively wordy. Or maybe I'll just have to bite the bullet and read sociology. Like, no offense to the sociologists out there, but it's not like you guys can't even describe on things like fundamentalism. A fundamentalist theory is like, oh well, society is like an organism, and like everything contributes to it like an organism. So it's like the government's like the brain, and then like the police are like the immune system, and then like everything else is everything else. And like, oh no, that's too simplistic. No, that's wrong because it doesn't like define this. It's like, okay, well, what's your theory? Oh, well, it's conflict theory. Basically, society is just like a constant like conflict for resources, and so it's like, yeah, and I'm like, so let me get this straight. Society forms because they're in conflict with each other, and it's like, okay, so are you saying that members within a single society are in conflict with each other, or are you saying that like societies are in conflict with each other over resources, and so this society is going in conflict with this society? And it's like, yeah, and then it's like, and then there's like the symbolic or whatever classification of sociology, where it's like, oh no, symbols form meanings through society, and it's like, just figure it out, sociologists. Dang. You know what the problem is? They can't ethically do any experiments. If we could get rid of ethics in science, problem solved. All of a sudden we'd have all these big answers, and we'd all go to jail. Yeah, so this is gonna be a long video. I'm probably running out of memory on my camera. But yeah, I'm gonna edit it tonight, and hopefully tomorrow afternoon you'll get it. And who knows, maybe I'll even be able to film something tomorrow night. Fingers crossed. But I hope you liked that, and my rambling, because this was 99% rambling. Yeah. Video requested by Jerem Lavretti. It's all you. I hope you're happy. You made countless others suffer through this. Well, not countless, like 12 others. Either way, yeah, good night, and sleep tight, and don't let the quantum mites